Once again, hello guys. Thanks for checking in again for another exciting video. This one, I wanted to make this one because I didn't think our textbook gave enough examples of how strong acids and strong bases might combine stoichiometrically, and the result being a pH of what's that, you say? Alright, so here we go. I'm just going to roll through a bunch of examples. Some of them go way back to chapter 3 of our text or something like that, where we imagine stoichiometric combinations of certain compounds. Specifically here we're talking about acids and bases and strong acids and strong bases. Anyways, so what if I had what if I had a 0.0573 molar nitric acid solution? Well, of course, nitric acid is a strong acid. So here's the first thing I noticed to myself is that being a strong acid, that creates also 0.0573 moles per liter of hydrogen ion, because 1 unit of nitric acid provides 1 hydrogen ion. Well, if this is the case, the question is actually pretty simple. The definition of pH is the negative logarithm of the hydrogen ion concentration, or the hydronium ion concentration, take your pick, because that proton's not just all by itself, it's with the water. But in any case, take the negative log of that, and you get 1.24185, etc., etc., etc. So that seems pretty simple, and it is. Before we go any further, though, let me mention the rules for sig figs and logarithms. When you find an answer to a logarithm question, this 1, or this digit in front, is kind of a placeholder. In a way, it's reflective of how many zeros came in front of this number. So here's 1 0, and that's the 1 right there. So believe it or not, if this number, 0.0573, had 3 sig figs, 3 non-zero digits, then these 3 here, the 2, the 4, the 1, those will count as the significant figures, not that one. So really, technically, if I report my answer for the pH of this acidic solution, 1.242. Interesting. Next example. What's the hydronium ion, hydrogen ion concentration if I have a pH of 4.17? Well, if they're so nice to tell us the pH, then we use the definition of pH and the reverse of the logarithm, and we just take 10 to the negative pH. So 10 to the negative pH gives me my hydrogen ion concentration. So if the pH is 4.17, just take 10 to the negative 4.17, and that comes out to something like 0.0000676 moles per liter. Yeah, it's pretty watered down. Than a pH of 4 you could certainly drink. Or well, we don't taste chemicals, but I'm just saying in terms of how much acid is in the water, I could imagine a 4.17 pH lemon water solution. That would be definitely consumable. Oh, just by the way, this wasn't part of the question, but we might also ask, if this is the hydrogen ion concentration, what's the hydroxide ion concentration? Remember, the Kw for water, 10 to the negative 14, must be the product of the OH minus and the H plus. So if I took that small number, divided it into the really small number, I get this molarity. Should be a capital M in back that, the molarity of the hydroxide. I could find the POH as well. 9.81, the negative log of that term. And the 9.81 plus the 4.17 should give you something, yes, very close to 14. It almost looks like a little rounding error here somewhere. I must have rounded this number off in my calculator. I could have kept it and gotten a more precise answer than 9.81. Anyways, this is the real deal up here. That's kind of a side note, but good to know, good to think about. What's the pH of a 0.0952 molar potassium hydroxide solution? Right away I see I've switched from acids to bases. So if this is a KOH, a hydroxide solution, won't the pH be 7? Below 7? Higher than 7? Yes, bases have a pH higher than 7. So anyways, if it's a strong base and I have 1 K and 1 OH, it's going to create the same number of moles per liter of hydroxide. The way I do it is I find the POH, that's the negative log of that hydroxide ion concentration. That's 1.021. Then I simply subtract that from 14. The definition of pH and POH lead me to this 14 number. Subtract the pH would be 12.979, which plus this should be equal to 14. Or I can work backwards if I like to find the hydrogen ion concentration. Oops. As well. Let's see. What's the pH of a 0.00153 molar strontium hydroxide solution? Well, let's think about that. Strontium hydroxide, that should be pretty simple, but look at this. There are 2 OHs for every unit of strontium hydroxide. So, if that's true, that's an important catch, an important realization, that the mole per liter concentration of this salt, strong base, would be only half as much as the hydroxide ion concentration, because one of these units creates 2 of the OH minuses. So that 2 should be taken into account. So my hydroxide ion concentration is really twice that number. It looks like 1.53 millimolar, come 3.06 millimolar. Except I can't really use the millis in my logarithm pH and pOH definitions. The pOH of that would be negative log of 0.00306, and that's 2.514, but therefore the pH is 14 minus that number. And the pH is definitely basic, 11.4. That'd be kind of damaging to tissues. You wouldn't want to touch that. Strontium hydroxide solution be very slippery and dangerous. Slippery, I say it's slippery because when you touch it with your fingers, do you remember in lecture I said it turned your skin into soap? Bases do that. What's the pH of a solution created by the dilution of 50 milliliters of 1.1 molar hydrochloric acid to a total volume of 750 milliliters? So let me think back to my dilution equation. I have a concentrated solution, 1.1 molar, 50 milliliters of it, and I'm going to water it down to 750 milliliters. So M1V1 equals M2V2, MAVA equals MBVB for acid and base, or concentrated and dilute. If I were doing a 1-to-1 titration of an acid and a base, I could use the same equation. But I go this one times this one divided by this one, and I find the new molarity, 0.0733 molar HCl. Well, from there, that's also 0.0733 moles per liter. I just take and that's it's strong acid, so it creates the same molarity of hydrogen ion. Take the negative log, that's the definition of pH, and the answer 1.13. Stuck a 4 there in case I wanted to carry it to a next calculation, but I don't think I do. What's the pH of a solution made by dissolving 0.057 grams of lithium hydroxide, a strong base, solid, into 500 milliliters solution? Well, the first thing you might think to yourself when you see grams is, change it to moles. You got it. So let me change grams to moles, and I can do this in one fell swoop if I'd like. My grams to mole calculation is that, 1 lithium, 1 oxygen, and 1 hydrogen. It's in 500 milliliters or 0.5 liters. There's the molar concentration of lithium hydroxide. Since it is a strong base, same concentration of hydroxide, and the pOH of that, negative log of that, and the pH of that, subtract that from 14. Oh, we've seen that before a few times already, and we're going to see it a few times again. What's the pH of a solution created by mixing 100 milliliters of 0.121 molar nitric acid, a strong acid again, with 200 milliliters of 0.0725 molar hydriodic acid? So that's a strong acid. Interesting. Remember the word of means times. So volume times molarity, volume times molarity. That's what I did here. And that gives me I didn't get rid of my millis. My milliliters give me millimoles. So I still have 12.1 millimoles of nitric acid, 14.5 millimoles of hydriodic acid. And since they're strong acids, that gives the same number of millimoles of acid, or hydronium slash hydroxide, not hydroxide, hydronium slash hydrogen ion. So the sum, if I were mixing them together, my total will be 26.6 millimoles of hydrogen ion. Now the volume of that was, it was 100 milliliters of this and 200 milliliters of this. So they kind of water each other down. The total volume is 300 milliliters. The millis cancel, this millimole and the milliliter cancel, and I'm left with this molar concentration of hydrogen ions. So all you'd have to do from there is take the negative log of that to find the pH. See, if you know the concentration of hydrogen ions, you can pretty easily and quickly find the Find the pH just by taking the negative log. What's the pH of a mixture of 10 milliliters of calcium hydroxide, 0.00253 molar, and 25 milliliters of rubidium hydroxide, 0.01257 molar? Well, if this doesn't ring a bell, I don't know what should, because it's very similar. And I took 10 milliliters times the molarity for calcium hydroxide, 25 milliliters times the molarity for rubidium hydroxide. I didn't get rid of the millis, so I still have millimoles. If I wanted to get rid of that, I could, but and I might have to. No, I shouldn't have to, because when I go to get my molarity, it'll divide by the milliliters, and the millis will cancel. But the realization here is that the calcium hydroxide has 2 OHs per unit. So if I had 0.0253 molar calcium hydroxide, it would actually be twice that number, twice that amount of hydroxide ions. So 2 OHs, that 2, this 2 gives this 2. And I find a total number of moles or millimoles of hydroxide, and I divide by the total volume. It was 10 milliliters of this, and was it 25 milliliters of the other? Total volume of 35 milliliters. Total molar concentration, moles per liter. Take the negative log, subtract it from 14, that gives you the pH. I'm speaking pretty quickly here, but you guys have the benefit of rewinding and restudying the videos. 35.71 milliliters looks like a titration of some kind. 0.812 molar hydrochloric is mixed with 50 milliliters of 0.225 molar NaOH. What's the resulting pH? I don't know. That's a strong acid and that's a strong base, so they react totally one way to neutralize. I took the volume times the molarity for both, and I found 29 millimoles of H plus ion from the HCl, 11.3 millimoles of OH minus from the NaOH. Then I take them and I put them in a table, something like this. So I created H plus and OH minus, create to give water. You know, I really don't care how much water I have. All I know is that the strong acid and the strong base go one way totally to react to give that. Since 11.3 is smaller than 29, the 11.3 will be totally consumed, and the 29 will only be partially consumed. If I had 29 millimoles of OH minus, it would certainly combine with 29 millimoles. There's a 1 there, there's a 1 there, to create 29 millimoles of water. But again, we really don't care how much water we have. So in any case, 11.3 goes all the way down. This goes up by 11.3 millimoles, but who cares about the water? We just care about what is left over in this mixture. And the answer is 17.7 millimoles of hydrogen ion left over. Interesting how that works. This is not like an ice table, but it's similar, isn't it? Here's my remaining acid in the water, the total volume between the two liquids that were mixed, and the new molarity, and you take the negative log of that. Voila, the pH. Very low pH. Still had quite a bit of acid. 17.7 millimoles left over in 85-ish milliliters, 85.71. One more example if I have time. What's the pH when I mix 100 milliliters of 0.0573 molar hydroxide, barium hydroxide, with 163.1 milliliter of 0.0591 molar nitric acid? Strong base, strong acid will react one way. Again, I take the volume times the molarity, but then I realize that this millimoles of barium hydroxide, I should take it times 2 because there's 2 units of OH for every unit of barium hydroxide. And similarly, but more easily for the nitric acid, since there's just one hydrogen ion, 9.64 millimoles of H+. So here's my strong acid, here's my strong base. Let's take and put them in an ice table of sorts. In the beginning, change is not equilibrium, it's in the final. So this one will go all the way down to 0. This one will go down by 9.64. This one will go up by 9.64, but who really cares about that? Here's my table filled in. This gets totally consumed to nothing. This gets consumed quite a ways down, but I still have 1.82 millimoles of OH minus left over. Consider the total volume, 100 milliliters of the base and 163 milliliters of the acid, if I had that correct, and the molar concentration. Take the negative log, subtract from 14. I'm out of time. Thanks, guys. Study these. I'll see you in class.